So bigger like this, or even a little bit bigger.
Okay, so I should try harder to write. Yes.
So I'm very glad to introduce my student, Dor Mezer, and his talk on multiplicity one theorems over positive characteristics.
So, hello everyone. Before I start the talk, I want to thank Professor Guy Enyart for because all of this project started from an idea that he kindly shared with Dima, my advisor, some years ago, and he allowed us and me to work on this project. I'm very thankful for that. Okay, so let us start talking about multiplicity one theorems and specifically over positive characteristics. So first, let me state the kind of questions that we ask, and that is multiplicity one theorems. Maybe I'll switch the marker. Is this better? So we are talking about representation of groups. So what kind of groups? We talk about groups, algebraic groups over a local field. So local field is either Archimedean, which is R or C. It can be a p-adic, which is non-Archimedean local field with over characteristic 0. And we have positive characteristic local fields, which look like finite field and some power series. So this is so these are the three kinds. And we'll talk about algebraic groups over these fields. So what is multiplicity one theorem? Multiplicity one property maybe is that when we have a pair of groups H inside G, we have the property that for any pi, which is an irreducible smooth representation of G, and rho is the same for H. We have the property that the dimension of the Hom space over H of the restriction of pi to H in rows is at most 1. So this is multiplicity one, the multiplicity one property we will consider. This is also called strong Gelfand property. And let me state some results. So there are many classical pairs which we will consider. So for example, we have maybe so we have GLN inside GLN plus 1. So this was proven in the So we have the Archimedean case. We have the p-adic fields case. And we have the, let's call it non-Archimedean and positive characteristic. I think the first thing that was proven from this table is Gn plus 1 for p-adic fields, and this is by Heisenberg and Gurevich in 2007. And yes, it was okay. So it was Heisenberg, Gurevich, Schiffman. It was in a paper of Heisenberg, Gurevich in which the proof was finished, but it relied on the work of Schiffman and Gralis. So it's really the work of all four of them. So this is the p-adic case, and then the table. Okay, so we also have in the Archimedean case two proofs, one by Heisenberg and Gurevich in 2008, and another one by Sun and Zhu in 2009.
It was actually simultaneous.
It was, yes, it was
simultaneous. We published it. Yeah.
Okay, so I just looked up the years that it was published, but it was two simultaneous proofs. So this is 2009. Okay, so let me write more pairs.
At least we put Schiffman and Gralis.
Okay. So also Gralis and Schiffman. So we have the pair of O inside O n plus 1. And also very similar to it, UN inside UN plus 1. In the Archimedean case, it's in the same paper of Sun and Zhu. And in the p-adic case, it's a paper by Heisenberg, Gurevich, Gralis, and Schiffman from also 2007. We have also the case of special orthogonal groups, SON inside SON plus 1. So this is again in the same paper of Sun and Zhu. And this Weizmann proved it in a paper in 2009. And another family, which is a bit different from this, I write two examples of it, not the general thing, but it's special, I'm sorry, SP, SPM, inside the semi-direct product of SPM with the Heisenberg group. So H, I think the indexing is also a and you can also switch it by the unitary group and some other version of the Heisenberg group. So I won't discuss it, so I'll just call it H prime. But there are a few more examples here. So this is also proven in the same paper of Sun and Zhu in 2009. And this is in paper of Sun in 2009. So what about the last column? About positive characteristic. So all of these proofs go more or less the same using a method I'll describe later. But here it wasn't known how to generalize this proof. And there is a proof only for the pair of Gn and Gn+1 by Heisenberg, Gurevich, and Sayat in 2007.
What's for special case? It was for each different problems. It was a case.
It wasn't the same as
this paper was only for trivial law.
Oh,
and for general law, it is Heisenberg Avni.
Okay, so maybe I mistook the paper. So it's Heisenberg Avni and Gurevich in, do you remember what year?
2009.
2009. So,
but the paper you mentioned is also relevant. It solves a special case when rho is trivial, but pi is any, and for GLN, but for all fields. This was also, I think, proposed.
Okay, so what this paper did is, correct me if I'm mistaken, but it took the case of a positive characteristic and reduced it to cases of zero characteristic. So instead of generalizing the proof, it generalized only the result. And this remained open, all of these. And in the project I'll not talk about all of these things, but at least I hope that I succeeded to prove all of these. In the in the positive characteristic case, but only when the characteristic is different than 2, so odd characteristic. I'll talk mostly about GLN and GLN+1. Because this is the simplest case, but the generalizations in the different cases are very similar to it. Okay, so first, just let me mention that these kinds of results have many important corollaries. So, namely, it shows uniqueness of Rankin-Selberg models, and this is I'm saying Rankin-Selberg models relying on a paper of Sun and Chen. It's called uniqueness of Rankin-Selberg properties. I think it describes how these results show it, and also these kinds of results show uniqueness of Bessel models and uniqueness of Fourier-Jacobi models. And this is by a paper of Gan-Gross and Prasad. All of these corollaries. So I think these maybe these three are related to Bessel models, and the last one, the last family actually, is related to Fourier-Jacobi models. Okay, so let's start talking about the proof. So the proofs of all of these results, except this one generalization, is using the technique of Gelfand and Kazhdan, which says that it is enough to find sigma, which is an anti-involution of G, which fixes H, and such that any add H in invariant distribution on G is sigma invariant. So the result says that if we find such an anti-involution and show this property for it, then we deduce the strong Gelfand and Kazhdan property for G and H. And that's what we want. So this is the method used. So actually, in most of these cases, it's very simple. The anti-involution itself is very simple. So in the case of GLM, this anti-involution is just A goes to A transpose. And yes, and then the theorem is just a theorem about distributions. It's showing that a distribution which is invariant to conjugation by GLM on GL plus 1 is also invariant to transpose. So maybe a stated theorem. So I write this curly S for the space of Schwarz functions, and this is for the space of distributions. So distributions on GL n plus 1 invariant to add GLN. Right side distributions on GLN plus 1, which are invariant to C. And so, okay, so I'll sketch the proof of this is a proof. Okay, so unsurprisingly, the proof over positive odd characteristic works also for characteristic 0. So I'll just tell maybe the general flow or sketch, if you want, of this proof. So the first step is really not that interesting. It's some reformulations. So okay, maybe I'm not. Maybe there is one thing which is a bit interesting in it. Oh, but I forgot. First, I want to tell two propositions about distributions. I mean, general propositions that I will use. These are propositions specifically for spaces for. I mean, it's specifically for non-archimedean fields, because these have a nice or not nice, depending on your point of view, a topology, which is called the topology of L spaces. So these are just two general facts about distributions on L spaces. And the first is the localization principle. It says the following. It says that assume that we have a map I from X to Y. These are two L spaces. And now assume that we have, okay, so we can consider distributions on X as an SY modulo. Right, because we can pull back a Schwarz function from y to x, and then multiply our distribution by that function. And now, okay, so assume that we have m inside distributions on x, which is an sy module. Then in this case, okay, so we can write the direct sum of all over all points y in y of the intersection of m and distributions on pi inverse y. And it turns out that this space is dense inside M. So what this principle tells us is that whenever we want to say something about distributions on X, in many times it is enough to consider distributions on fibers of some map from X to Y, because let's say that we want to show that any distribution which satisfies some property satisfies another property, then in most cases distributions that satisfy this property are described by module M. And then if we know that this is dense, these spaces of distributions on fibers, if we prove some continuous property for these, it will also be true for all elements of M. So this is one very useful property. The second one is called Frobenius descent. And what it says is that, okay, so we also start from a map from X to Y, but this time we assume it is onto. And we also assume that we have an action of a group G on both X and Y. So G acts, let's say that it acts on pi. So pi is compatible with the G action. And now assume that also we have a character chi. So it's a character of G. And assume that we are interested in the space of distributions on X such that G acts with the character chi. This will be our notation for that. Then it's naturally isomorphic to the space of distributions on pi inverse y, where y is just some point in y that we choose. It doesn't matter which. And here we write the stabilizer inside G of y, again with the character chi. So is there a question?
It can be twisted by modular functions.
It can twist by modular functions.
Yes.
Okay, so
This character chi prime.
okay, so let's just write chi prime. I also assume that G is unimodular. Is that what you meant?
But this, then you need also the stabilizer to be.
Yes, okay, so I just add the conditions that G and the stabilizer are unimodular. So we assume this, and then we get this isomorphism. And now hopefully this statement is correct. That's, So, yes, I forgot another condition, and that is the action of G on Y is transitive. So, G on Y is transitive. Thank you. Otherwise, of course, this doesn't make sense. Okay. So these are the two main tools that I will use, which are specific to distributions on L spaces. So now let me sketch the flow of the proof. Okay, so first we want a bit of reformulations of the problem. Okay, you know what? Before let me stop and ask: are there any questions? Maybe this is a good point.
Excuse me. Can you please explain again this isomorphism? Is it a distribution on a single fiber?
Yes, exactly. It's distributions on a single fiber. So basically, the arrow from the right to the left is given by induction.
Okay, G is a transitive action. That's why. Okay, I see. Mm-hmm.
Yes.
Thank you.
Okay. So, any other questions? Okay. So the first step is a bit of reformulations. So. Let's recall that this is the original formulation of the theorem, and so first is reformulations. And the reformulation of the theorem that I mean, it's in the original proof also, is that it's enough to prove that distributions on the Lie algebra GLM. So because we don't want to use basis every time, we assume that we have an n-dimensional space V. So actually, we say here GL of V times V times V star. And we have an action of this. Okay, so I write it and then I explain what it means. So G tilde and the character chi is equal to 0. So first, what is G tilde? It's just the G tilde is semi-direct product of G and just plus minus 1, the group of two elements. And it is basically what is generated by G and by, so here G is GLN. By GLN and sigma. So if we apply sigma, then conjugate by an element of GLN, then apply sigma again. It's like we conjugated in, I mean, it's like we, so yes, it's like we conjugated in an element which is the inverse transpose of the original element. So it defines a semi-direct product like this. And the character chi is just this last sign. So this is chi. And now, instead of saying that n distribution on which is GLN invariant is also G tilde invariant, this is the same. we can say that any distribution which is g tilde chi equivariant is 0. And that is because we can just take a distribution, subtract from it its transpose, and we want to show that this is 0, but this is g tilde chi equivariant distribution. So it's not. So I explained this part. Now for this part, we have. So this is n plus 1 times n plus 1 matrices. But the action is action by blocks. So we actually have the last row and the last column. And here this just one entry. And the action is on every part by itself. Now we can get rid of this last entry by localization principle. So we separate each possible value, and then all are the same. So we just ignore it. And then we have a GL of V times V times V star, because this column vector is naturally in V, and this row vector is naturally in V star. And this is, of course, a matrix in GLV. And now maybe the only interesting thing, which is, again, not hard to show, but it will have an impact, is that we pass from just invertible matrices to all matrices. So this is a nice trick. We'll use it later. But right now, we just formulated this like that. So it's enough to show this instead of the original statement. Okay. And now we get to the maybe I don't know if this is the main step, but one of the main strategies. So it will be to assume that we have g tilde chi equivariant distribution and restrict its support. So from now on, I will always assume that we have a distribution. So call it I don't know psi, and for we will denote a point in its support by a v phi. So it's inside the support of psi, which is inside GLV times V times V star. Okay, so we want to restrict the support. So what can we do? We can look on V and phi, and there is a well-defined pairing, which we will denote by V phi. Now we can use these two tools on this pairing. So first we isolate different values of this pairing, and then any value which is not 0. It turns out that we can use Frobenius descent to reduce to the same claim, but in one dimension smaller. So we can use induction and then assume that it is 0. So actually, we show here that for any such point in the support, this pairing must be 0. So this is a key claim. And now, okay, so we have some restriction of the support, but we want to restrict it even further. So what is the strategy? We have a standard restriction. So we can think of it like a cookie cutter. And then we can cut it one way, but if we will rotate our cookie cutter and then cut again, we will restrict even further. So the tool that we use here is automorphisms. And we want to find some automorphisms of all of the problem, and then apply these automorphisms, and then use this claim to restrict the support even further. So, which word have we used? So actually we'll have two kinds of automorphisms. The first, let us denote it by mu, and it will have a parameter mu. And what does this do? It takes a v and phi to a plus v tensor phi. Oh, or here we can insert mu, v and phi. So this is compatible with all of the action of g tilde on these spaces, and it's also invertible. By applying nu minus mu, it gets back to a v phi. This is the first, and the second is a row of f. Here f is a polynomial, so here mu is a scalar in mu inside f. F is the field which we are working over, and rho f it will be defined as a v phi goes to a f of a v f of a star phi. So here f is a polynomial. And this is also compatible with all of the actions, but there is one little bit annoying point, and that is it's not evident why it's invertible. But actually we can overcome this problem by saying that we can first use the localization principle to talk only about one characteristic polynomial of A. So we separate all the possible characteristic polynomials of A. And then if we take f, which is co-prime to the characteristic polynomial of A, then this is invertible. We can find another polynomial such that on this fiber it will be the inverse. And it turns out that this is good enough. So what happens if we, okay, so if we want to use the first to amplify this condition, we will get nothing, right? Because we didn't touch v and phi. But if you use the second, we get that f of a v and f of a star phi is 0. So a priori, we know this only for some Zariski open set of polynomials, but since this is an algebraic condition, we actually know it for all polynomials. So, okay, so what does this say? It's actually just, so this is equal to f of a squared v and phi. And now, actually, I claim that this implies that ak v phi is equal to 0. And why is that? So we can write it as half of a to the 2k. So maybe a to the k plus 1 squared v phi minus a to the k squared v phi minus v phi. And actually, this half is where we use the condition of odd characteristic. So this 1/2 is really doesn't work over characteristic 2. Actually, if it's interesting, I don't know. I think that I found a way to overcome this characteristic 2. So there is another proof of this property, which is it's a bit more involved. I won't talk about it, but yes. So we show that a to the k v phi is equal to 0. This is 0, and this basically shows that for all polynomial we have that f of a v phi equals 0. Okay. So using the automorphisms, we strengthen this condition to show that for all k, a to the k v phi is equal to 0. And now it turns out that this is a very nice property. So we have a lemma. Let me here maybe. Lemma.
So do you actually need all polynomials, or are you just happy with some very small number of polynomials?
So I actually need all polynomials.
You need that?
Yes. And this is because of the following lemma. So what it says is that this condition of for all k a to the k v phi equals 0, this condition is equivalent to the condition that the characteristic polynomial, so we denote it like that, the characteristic polynomial of a plus mu v tensor phi is equal to the characteristic polynomial of a. So this is true for also. I mean, this equivalence is true if you write here for a single non-zero mu or for all mu. Actually, it's very easy to see that this is in general linear in mu. So also the derivative at 0 is enough. And you can see that the importance of this lemma by that we have nu of mu. What it says is basically that nu of mu it preserves. It's an automorphism which also preserves the characteristic polynomial. And this is very, very nice because okay, so I wrote here 3, but maybe it's I don't know 2.5. So the situation now is that we restricted the support of it, and we still have this automorphism nu, which we didn't use, and we know that it preserves the characteristic polynomial. So now we can actually separate each characteristic polynomial. We could do this before, but we didn't want to, or I mean, this is convenience matter. Using the localization principle, so we separate it. And then the next thing that we want to do is to use Frobenius descent on the map to A. And what is the situation? We have, again, triples A, V, and phi. But now A is with a specific characteristic polynomial. And this space in which A lives is a space with finitely many G orbits. So G tilde orbits is the same. So if we have finitely many G tilde orbits, then we can use what is called the method of stratification. To reduce to a single orbit. And, I'll say in a few words what it is. It's not very, it's actually quite simple. And then on a single orbit, we can use Frobenius descent. So what is stratification? It's just the following thing. You can restrict to an orbit of maximal dimension. It is an open orbit, so restriction is a good operation here. And then talk about what we have, apply nu, and show that on this orbit, the distribution we have is 0. And then once we know that it's true for orbits of maximal dimension, we are supported on orbits of smaller dimension. And then we can restrict to an open orbit there. And once we restrict to an open orbit there, we also have this condition that nu keeps us inside these orbits and don't get us to larger orbits. So this is also very useful. And so on. So we restrict to a maximal orbit that we still have, and show that some property on this orbit, and then this will reduce to smaller and smaller orbits until we are done. So this is the method of stratification. So let me just write it. It's with respect to orbits. Now we have the claim for a single orbit. So we want to show that if we have a distribution on a single orbit, so if we have distribution on a single orbit, then okay, so we have some conditions. I won't state all of them, but it's basically this. I think that we prove. And we want to show that any such distribution, again with the equivariance to G tilde and chi, that any such distribution is 0. So how do we apply Frobenius descent? So we can just apply Frobenius descent to the map of A, V, V star goes to A. So because we're restricted to an orbit, the space of such possible A's is G tilde transitive. And okay, so what is the fiber of this map? So the fiber is actually V times V star. So we have distributions on V times V star. Let me write that. So it's not G tilde, it's some G tilde A. G8 in the maybe height.
And they also satisfy these conditions?
Yes, so actually there is a technical point there, which is a passage to a bit stronger condition and then back to these conditions. So we really want the condition that not only keeps us inside this characteristic polynomial, but that it doesn't get us to larger orbits. So we can say that in terms of V tensor phi is inside the tangent space to A of the orbit. And so this is just a. So this is actually the stronger condition that we pass to. And it's for, I think, a technical reason. But it's very closely related to this condition. Okay, so we pass through the orbit. We use the Frobenius descent. And now we have something of this kind to kill. And now comes in the last hammer which we use. And that is Fourier transform. So actually you could say long before that, but then maybe we didn't see why we need it. But now, okay, so actually before even the stratification, we could apply Fourier transform on the distribution. We could apply Fourier transform just on the last two coordinates. We have a bilinear product thereby defined by pairing. And this Fourier transform also satisfies all of the equivalence conditions, because I mean it switches with it commutes with the action of G tilde, and here we also apply Frobenius descent. Actually, it also behaves nicely with Fourier transform. So all of these restrictions of the support are not only on the distribution itself, but also on its Fourier transform. But in this case, we have a general principle, which is maybe the Heisenberg's uncertainty principle, which says that if a distribution or a function, whatever, has small support and also its Fourier transform has small support, then it must be zero. So I won't state the exact theorem of this kind that we use here, but it's a theorem of Rallis and Schiffman. Rallis with two F's. Schiffman. So that's
It's two ends.
two ends. So it's one of their ideas. I mean, important ideas which are used in this proof. So this is the aspect of Fourier transform. Yes, there is one step which I hide between these things, and that is here we talk about any operator A, and there is a way to restrict it to. Okay, so I can say Jordan blocks, but we don't assume that our field is algebraically closed. So we actually use rational canonical form. So we restrict to these simple blocks. And then I said this condition is technical because it's used only for the passage from general A's to just simple kind of A's. Just by showing that if it's true for A1 and A2, then it's also true for A1 plus A2, which lives in larger dimension. And then we go back from this condition to this condition, that for all k, we have this. So yes, this is the flow of the proof. Are there any questions?
What was the last step? Use Fourier transform.
So use Fourier transform to, okay, we have, we talk about distributions on 3 times V star, right? But we have a restriction on the support of these distributions. And that is basically this condition, that for all k, we have AKV, comma phi equals 0. But actually we have this condition not only for the distribution itself, but also for its Fourier transform. So I didn't explain all of the details, but it turns out that that if you have this restriction on both the distribution and its Fourier transform, then it says that the distribution, I don't remember if it must be 0 already, or that it must be some specific distributions, some specific some R measure or something like that, which then we know by hand that it's also invariant to this involution. So, any more questions? Dima, how am I with
You have 2 more minutes.
I have 2 more minutes. Okay. So, not sure if there is. Oh, there is one more thing that I want just to comment about, and that is where this differs from the proof in characteristic 0. So the point of divergence here is, I mean, it's already in step 2. In the characteristic 0 setting, another method was used, and that is the method of Archimedean descent. And this is so this is basically using Jordan decomposition, which is A equals A semi-simple plus A nilpotent, and then the map which maps to A semi-simple, and it uses this map with I mean, it uses this map to apply Frobenius descent, and then again by some kind of induction, it reduces to the nilpotent cone. So instead of this condition, there is the condition that A is nilpotent, and this is the restriction used there. And then instead of rho wasn't used there at all, and instead just nu was used to claim again this condition, because then we knew that also both A and A plus mu v tensor phi are both nilpotent, and this by the lemma here implies this condition. So again, we had this condition, and from there on, the proof was very similar. So all of the stratification and what we have for single orbit is very, very similar. Only here we have to deal with a little bit more cases, because we don't only have nilpotent orbits, but maybe also other orbits. And this flow is basically what happens in not only for GLN inside GLN plus 1, but all pairs which I described earlier. And again, the changes are very, very similar. So in all cases, reduction to the important cone is replaced by just by this condition, and then the automorphism rho to amplify it to this condition. And again, the very end is a bit different because we have to consider all orbits and not just important orbits. But actually, it turns out that important orbits are the hardest. So it's not harder work. It's just stating a bit more.
You cannot use acoustics. Why don't you follow the acoustics?
Oh, yeah, I didn't say that. Simply, Jordan decomposition fails over positive characteristic. When we have A and its characteristic polynomial is non-separable, then this decomposition just fails badly. So it can be used to some extent. I didn't use it here, but it can be used to some extent to instead of restrict to the important cone, restrict to A's which, as characteristic polynomials, have a single irreducible factor, and this irreducible factor is purely inseparable. So this can be done, but I don't know. I mean, I don't see how more than this can be done using this method.
Thank you very much. More questions, please?
Thank you very much.
There were a couple of questions during the class. So it's
Okay.
And the next talk is in 2 weeks by Jutta Handel. I will send the announcement when I was there. So comments on this format are also welcome. You can write me an email and say that it was better than usual, or not better. Okay, so see. And so in general, in June and July, we will continue on a bi-weekly basis. So we will have a talk on June 30, and then on July 14 by Kazhdan, and then maybe one more talk in July, and have a break for August, September, and I start. Okay. See you everyone in a couple of weeks.
זה אין חיובי גם יש מספר, כאילו אין מספר סופי של ציונים.
Yes, so the main difficulty is that there are infinitely many orbits. So we cannot just restrict to important orbits. For GLN, there are finitely many important orbits. Also, yes, well, GLN doesn't care. It's Jordan form. I mean, it's not Jordan form. It's it's just partitions. But you cannot restrict to important core. I mean, it depends what you call important. Yes. I mean, you don't have such a decomposition to restrict an important cone, and the main input was to go around it.
And also, you didn't have this, did you?
We didn't introduce these ones.
Like the
row
and the OF?
So new was
New was our input. With respect to Rice and Schiffman, our main input was the automorphism. But raw, we also thought about them, but they didn't find a way into all. And I think in O and in the orthogonal unitary case, you have some more automorphism. Similar to raw, but a bit different, right?
No, it's just a version of raw. It's not something new. It's just raw, but it's a bit more annoying to define.
Okay.
I'm saying for which polynomials f, it's okay to consider raw f.
So for all it's same idea, but more technical, and you use also K-lemma, right?
Yes. So there is the linearization part, which I didn't at all talk about, but in GLN it's easier, and in O it's.
So in GLN you use the group as an open subset of the Lie algebra.
Yeah.
And in O you use the K-lemma.
Okay. If watch ones and other like other groups, well, with like similar statement, you don't have like way first yet.
Similar to this, I don't know.
So for O, U, SO, SP, of course, the K-lemmas.
Okay. Remember that there's like only thing, so is there also K-lemma for this?
Yes.
Remember like there's something for O and S or something.
No, it's I mean, if you just write the proof, it's a proof that if A star equals A inverse, then the K-lemma of A star is equal to minus itself. That this just it just formally works.
Yeah, I'm not surprised.
So Vitek Gan recently explained that the Killing map is actually a change of coordinates. So you take G modulo Z parabolic, and
Never mind what is here.
so stabilizer of Lagrange. And there are two ways to look at it. To open that subset. And these two open that subsets intersect, and change of coordinate is given.
Should we stop the YouTube?
Yeah, I see. You should disconnect. So if anyone has some question, it's the last opportunity to ask.